Hello everyone, I am Samir and I'm going to be presenting our work on Byzantine consensus with local multicast channels. This is joint work with Professor Nitin Vaidya at Georgetown University. Let me introduce the setting. There are n nodes in a synchronous system with binary inputs. They want to reach consensus on a common value. However, up to f of these nodes can be Byzantine faulty. These nodes exhibit faulty behavior and can deviate from the protocol arbitrarily. The end nodes communicate by passing messages to each other. The communication network is captured by an arbitrary undirected graph G. To solve consensus, we require that all the non-faulty nodes must output the same value. To prevent trivial solutions, we require that this output value must come from an input of a non-faulty node. And we require that the consensus algorithm must terminate in finite time. In this work, we are interested in finding the tight network requirements for consensus to be possible. This depends upon the communication model being considered. Different models have been considered before in the literature, which include the point-to-point communication model, the local broadcast model, as well as using hypergraphs to capture communication channels. For each of these models, tight conditions are already known. In this work, we introduce the local multicast model, which generalizes each of these three models, and we obtain tight network conditions for consensus in this model. The classical model that has been considered before is a point-to-point communication model. Suppose node U has two neighbors V and W. In this model, when node U wants to send a message to node V, it is private between U and V, so that node W does not overhear this communication. So now you can possibly send a different message to node W which conflicts with the initial message sent to node V. So in this example, U sent a message MA to node V, and it is sending a different message MB to node W. This allows a faulty node to send conflicting information to its neighbors. This ability is called equivocation, and it is enabled by the privacy afforded by the point-to-point communication model. In the graph G, each edge represents a FIFO point-to-point channel. Whenever a node receives any message, it can identify the sender of that message. For instance, in the example on the right, when V receives the message MA, it can identify that the message MA was sent by the node U. In contrast, in the local broadcast model, when a node sends a message, it is received identically by all of its neighbors. For instance, in this example on the right, when U sends a message M, it is received identically by both of its neighbors V and W. In the local broadcast model, faulty nodes cannot equivocate, since every message is received identically by all of its neighbors. As before, each local broadcast channel is a FIFO channel, and on receiving a message, the recipient can identify the sender ID. When the communication graph is complete, then this corresponds to the global broadcast model, where every message sent by any node is received identically by all the other nodes in the system. In this paper, we consider the local multicast model. In this model, each message is transmitted on a local multicast channel. A local multicast channel is defined by a single sender S and multiple receivers from its neighbors in the communication graph. For instance, in the example on the right, the node S has three neighbors U, V, and W. From these neighbors, the blue local multicast channel has two receivers V and W. Whenever a node sends a message on a local multicast channel, all the receivers in that channel receive the same message. This prevents a faulty node from equivocating on the same multicast channel. However, a faulty node can still equivocate across different channels. Each multicast channel is a FIFO channel, and on receiving a message, the recipient node can identify the channel ID on which the message was sent. A faulty node can still equivocate in the local multicast model. However, the equivocation is restricted by the local multicast channels in the graph G. For instance, consider this example where node V has three neighbors U, W, and Z. V has two local multicast channels, a blue channel and a red channel. The blue channel has two recipients U and W, while the red channel has two recipients W and Z. Node V can pretend that it has input 0 when communicating on the blue channel and pretend that it has input 1 when it communicates on the red channel. Now, node W is part of both red and blue channel, so node W will be able to identify that node V is lying across the two channels. However, the nodes U and Z cannot directly identify that node V is lying. In the point-to-point model, a faulty node could equivocate between any two neighbors. In this setting, it is well known that at least 3f plus 1 nodes and 2f plus 1 node connectivity is both necessary and sufficient for consensus in undirected graphs. In the local broadcast model, a faulty node cannot equivocate at all. In this case, the network requirements improve to degree at least 2f and connectivity 3f over 2 plus 1. The third model of interest here is the hypergraph model. In this model, any node on a hyperedge can act as a sender, and messages sent on a hyperedge are received identically by all nodes in the hyperedge. So the non-equivocation is captured using the hyperedges. The tight conditions are also known for this model. The local multicast model encapsulates all three of these models. The point-to-point case is on one extreme where all channels have a single receiver, so the message is private between the sender and the single receiver. The local broadcast model is on the other extreme where each node has a single channel, so for any node, all of its neighbors are in the same channel. The local multicast model corresponds to the hypergraph model when the multicast channels are induced from the hyperedges. The tight conditions that we identify in this paper reduce to the corresponding known tight conditions in each of these three cases. Let's look at this example one more time. Node V has two multicast channels, blue and red, and we can pretend to have input 0 on the blue channel and pretend to have input 1 on the red channel. To capture this sort of equivocation, we use node split to capture this behavior. Splitting a node V intuitively replaces it with two nodes V0 and V1. Furthermore, the multicast channels of V are divided between V0 and V1. Observe that there is a choice of where each multicast channel is assigned in the split operation, and this is useful later on. We additionally create a point-to-point channel between V0 and V1. Let's look at how node split can be applied to the previous example. Node V has two channels, blue and red. When node V is split, we create V0 and V1. And now one of the options is that blue and red channels can be assigned to V0 and V1 respectively. This gives us a graph G'1, where the blue channel is assigned to V0 and the red channel is assigned to V1. On the other hand, if both channels are assigned to V0, then this gives us the graph G'2. And if both channels are assigned to V1, then this gives us the graph G'3. The split operation can be generalized to a set of nodes as well. To split a set of nodes X, we split each of the nodes in X individually one by one. The order of the split does not matter. In this case, each node V in X will be split and replaced with two copies V0 and V1. Each channel of V will be assigned to either V0 or V1, and this creates a new graph G', and we use V' to denote the node set of G', and we use E' to denote the edge set of E'. As mentioned before, we are using this split operation to capture the possible equivocation by faulty nodes. So consider a candidate faulty set F. We use lambda F of G to denote the set of all graphs that can be obtained by splitting some subset of nodes in F. Observe that each G' in lambda F of G is obtained by firstly choosing which nodes in F to split, and secondly by assigning the multicast channels for each split node. For G', we use F' to denote the nodes in G' that correspond to the original candidate faulty set F in G. Before presenting the tight condition for the local multicast model, let us introduce some notation. For two disjoint sets X and Y, we say that a set X is adjacent to set Y if Y has at least F plus 1 neighbors in X. We denote this by using an arrow from X to Y. To see what this adjacency condition is trying to capture, suppose all nodes in Y have input 0. If Y does not have F plus 1 neighbors outside, then nodes in Y have no choice but to output 0. So the adjacency condition is trying to capture when nodes in Y can move from their initial position. Based on this intuition, we can come up with a necessary condition. For every possible faulty set F and two disjoint sets L and R, we require that either non-faulty nodes in R have enough neighbors outside of R, or non-faulty nodes in L have enough neighbors outside of L. If this is not true, then nodes in R cannot move from their initial position and nodes in L cannot move from their initial position, so they're both stuck at their inputs. This condition, however, does not capture the possible equivocation by faulty nodes. So we can actually make this stronger by using the node split operation. In this case, we now require that for every possible faulty set F, we look at the graph G prime obtained by splitting some nodes in F. Now for two disjoint sets L and R in this graph G prime, we now require that either the non-faulty nodes in R have enough neighbors outside of R in G prime, or non-faulty nodes in L have enough neighbors outside of L in G prime. In this paper, we show that this condition is in fact tight, that it is both necessary and sufficient. This condition is actually very similar to network conditions for directed graphs for the point-to-point and local broadcast communication models that have been looked at in the literature. Even though we are working with undirected graphs, the local multicast model is quite general and it captures various models with different connectivity requirements. So it is plausible that no concise network property will be able to properly characterize the local multicast model. In the rest of the talk, I'm going to give a quick overview of the necessity and sufficiency arguments. For necessity, let's pick a graph G prime obtained by splitting some possibly faulty nodes. For the necessity argument, we show that there is no consensus algorithm for G prime using the state machine based approach. We now want to show that this also implies that there is no consensus algorithm for G either. So what we do is we show the contrapositive that an algorithm for G will imply an algorithm for G prime. However, this is not strictly true, but we are able to show something slightly weaker. We show that a consensus algorithm for G implies an algorithm for G prime that solves consensus in a slightly restricted sense. In particular, we show that as long as two conditions on the execution of G prime are satisfied, then the algorithm for G prime will solve consensus. The first condition is that for every split node V, either both V0 and V1 have the same input, or at least one of them is faulty. The second condition is that the faults in G prime should correspond to at most F nodes in G. We ensure that both of these conditions are met in the state machine based argument for necessity, and so the argument goes through. Intuitively, the first condition is saying that if both V0 and V1 do not have the same input, then they're acting like a faulty node and they should be treated as such. And the second condition is saying that the faults should not that there should not be two more faulty nodes than what the original algorithm for G was designed for. So the faults in G prime should not go over the budget of F nodes in the original graph G. The adjacency conditions are useful for necessity proofs. For sufficiency proofs, we need something slightly different. For two disjoint sets X and Y, we say that X propagates to Y if for every node V in Y, there are at least F plus 1 node disjoint paths that start from X and end at V. We also require that these paths should only use the nodes in X and Y. We denote this by using a squiggly arrow from X to Y. Now the adjacency based conditions that we gave earlier are actually equivalent to a propagates based condition that I'm going to present next. For every possible faulty set F and a graph G prime obtained by splitting some nodes in F, we require that every partition of G prime into two sets A and B should satisfy the following. Either A should propagate to nodes in B minus F prime, or B should propagate to nodes in A minus F prime. So either A propagates to non-faulty nodes in B, or B propagates to non-faulty nodes in A in the graph G prime, which is obtained by splitting some nodes in F. To see what this looks like, suppose we have a graph G prime that is obtained by splitting some nodes in F. And we partition G prime into two sets A and B. Now suppose that A propagates to non-faulty nodes in B. Right? This means that for every non-faulty node in B, there are at least F plus 1 node disjoint paths that start from A and end at V. Also, these paths cannot use the faulty nodes in B, and that's because the paths are restricted to using the nodes in A and the non-faulty nodes in B minus F prime. So this corresponds to G minus B intersection F prime. So these paths cannot use the faulty nodes in B. So for example, in the picture on the left, here is V, and there are F plus 1 paths that go from A to V. These paths can have source nodes from F prime because they are originating from A, but they cannot have internal nodes that are in both B and F prime. In the rest of the talk, I'm going to focus on the algorithm that we use to show the sufficiency of the propagate-based condition. In the algorithm, every node V has a state variable gamma V, which is initialized to the input of the node V. The algorithm considers every possible candidate faulty set F, and in each iteration, the nodes in G minus F attempt to reach consensus by exchanging their state variables. At the end, each node outputs its state variable, and we show that this output of gamma V actually satisfies the agreement and validity conditions. To ensure that the gamma value is never updated to a bad value, the algorithm has some safety checks. A value gamma V is updated only if it is received along at least F plus 1 node disjoint paths from at least F plus 1 different source nodes. This ensures that any value that is updated must have come from a non-faulty node, because there are at most F faulty nodes, so one of these values must be coming from a non-faulty node without being tampered. This ensures the validity property. Crucially, this also ensures that an agreement once achieved is never lost, because if all non-faulty nodes reach an agreement, then because I'm only updating a value to something that was already there at a non-faulty node, I'm guaranteed that the agreement that is once achieved is not going to be lost in the future iteration. To make progress, we ensure that in the iteration when the candidate faulty set is the actual fault set, then all the non-faulty nodes reach agreement in this iteration. Together with the safety condition, we ensure that in at least one iteration, nodes will reach agreement, and this agreement will stay on until the end of the algorithm. So remember that in the algorithm, we're considering every candidate faulty set, and we're trying to reach consensus in G minus F in this particular iteration. So in the rest of the talk, I'm going to focus on explaining these steps. So fix a candidate faulty set F and the corresponding iteration of the for loop. I'm going to explain how the consensus is attempted in this particular iteration. So each node V floods its gamma V state variable. What this means is that each node V is going to transmit its gamma V state variable on all of its multicast channels, and its neighbors are going to forward it and so forth until every node receives this value. Now, of course, a faulty node might equivocate, or a good node's value might be tampered with, so it's not guaranteed that this value is received reliably by every other node. But based on the messages that are received during flooding, each node V takes the following step. It creates a graph G prime V by splitting all the nodes in the candidate faulty set F. Based on the messages that are received during the flooding process, it also assigns the channels in the split operation. And then it partitions this G prime V into two sets Z, V, and N, V. These sets are approximations of the sets Z and N, where Z is intuitively all the nodes which flooded 0, and N is all the nodes which flooded 1. Now, of course, the faulty nodes might equivocate, so we assign U0 to Z and U1 to N, because the split operation is intuitively capturing this equivocation. Crucially, we maintain the following property, that when F is actually equal to F star, then every node V will take identical steps. This means that every node V will create identical split graphs, and every node V will have the correct approximation, the correct evaluation of the Z and N sets. So every node V actually takes identical steps when F is equal to F star. Nodes rely on the propagates-based condition to update their gamma V variable. So if Z propagates to the non-faulty nodes in N in G prime, then the non-faulty nodes in N are going to see if they should update their state to match the state in Z. So suppose that V propagates to the non-faulty nodes in NV in the graph G prime. Then we will check if it received 0 identically along f plus 1 node disjoint paths that start from ZV and end at V. Since if this is true, then it's going to update its gamma V variable to match the state in Z, which is 0. Similarly, if NV propagates to ZV minus F prime, then it's going to do the symmetric, then it's going to update its gamma V variable to 1. Now, since it's only updating its gamma V variable if the value was received along F plus 1 node disjoint paths, then we have the safety property. So one of these values must be coming from some non-faulty node. We also ensure that when F is equal to F star, then every non-faulty node in N does the same thing and updates its gamma V variable to 0. In the else case, every non-faulty node in Z updates its gamma V state variable to 1. So everybody at the end of this iteration, when F is equal to F star, every non-faulty node will have the same state, and that gives us agreement. And because it's only updated along F plus 1, if a value is received along F plus 1 node disjoint paths, so that gives us safety. So to summarize, in this work we have introduced a local multicast model which generalizes different known models that have been considered before in the literature. We use the node split operation to capture the non-equivocation that exists in this model. We give tight conditions to solve the tight conditions for consensus in this local multicast model. We use the adjacency based view for the necessity argument, and we use the propagation based view for the sufficiency argument and for the algorithm. Thank you for watching.